In this video, I'll talk about the quantum mechanical postulates for the hydrogen-like atoms or ions. For example, helium plus, lithium 2 plus, beryllium 3 plus. They all have only one electron, but they have different number of protons. Helium, lithium, beryllium have 2, 3, or 4 protons in the nucleus. The Schrödinger equation is H psi equals E psi. So we write out the Hamiltonian operator H over here. It's the sum of the kinetic energy operator and the potential energy operator. We neglect the kinetic energy of the nucleus because it's much smaller than the kinetic energy of the electron. Over here, the attraction is between the single electron E and the Z protons in the nucleus. Z is the number of protons in the nucleus. We convert this Schrödinger equation to the atomic units right here. H bar is 1, the mass of the electron is 1, the charge of the electron is -1, -1 squared is 1, and 1 over 4 pi epsilon is 1. And then we have a simplified Schrödinger equation here. We cannot solve this equation directly because R is the square root of x squared plus y squared plus z squared. We cannot separate x from z or y. Therefore, we convert this into r, theta, phi polar coordinates right here. This equation looks much more complicated, but it's solvable. After we solve this Schrödinger equation, we'll see. When we're talking about principal quantum numbers, n can be 1, 2, 3, 4, etc. When n equals 1, we have only one s orbital here. The wave function of the 1s orbital is e to the power of -zr. Remember, for the hydrogen atom, the wave function is e to the power of -r. Now we have z protons. The wave function becomes e to the power of -zr. When you have a larger number of z, this function decays faster. The energy of the 1s orbital in this z proton hydrogen-like atom or ion is -z squared over 2 atomic unit. More generally, if we're talking about different principal quantum numbers, again, n can be 2, 3, 4, etc. The energy of this n sub n is equal to -z squared over 2n squared atomic unit. Again, for the hydrogen atom, E sub n is simply -1 over 2n squared. Now I will use the 1s atomic orbital to illustrate the first 4 quantum mechanical postulates. The equation is e to the power of -z times r. Postulate 1. This function is single-valued, continuous, and finite. Postulate 2. Every physical observable has a corresponding operator. Postulate 3. For every physical observable with a corresponding operator A, if this function, this wave function, happens to be the eigenfunction of the operator A, and then we will obtain a eigenvalue lowercase a. This lowercase a is the value of the physical observable. So we're going to look at this postulate 3 in more detail. I will now prove that this 1s orbital of the hydrogen-like atom or ion is indeed an eigenfunction of the total energy operator, and then we will get the eigenvalue. So we're going to apply this h to this wave function. H is the sum of the kinetic energy operator, which is here, and the potential energy operator, which is here. So we apply the kinetic energy operator to the wave function and also the potential energy operator to the wave function. Fortunately, this wave function does not contain theta or phi. It does not depend on theta or phi. Therefore, we have only one term here being applied to this wave function as the kinetic energy part right here. And then this is the potential energy part, which is much easier. Now we need to take the first derivative over here, d over dr to this e to the power of negative zr. Again, we have 1, 2, 3, 4 operators. We apply this operator first to this wave function because this operator is the closest to this wave function. And the first derivative of this function is negative z times e to the power of negative zr. So remember, we have a negative z here. Negative z multiplied by negative 1 is z. Therefore, we have z over 2 in front. And then we apply the second operator. Just view this r squared as a operator. And this is a multiplication operation. So we'll just do a product here. The third operator, d over dr, we're going to use the product rule. The first derivative of r squared is 2r. The first derivative of this exponential function is negative z times this exponential function. So we have two terms now. Again, we just copy this potential energy operator being applied to the wave function. So in total, we have three terms. We'll simplify the first two terms. Again, we divide this two terms by r squared. We get this two terms. And after some more simplification, we got three terms here. The first one is equal to the third one, but with an opposite sign. Therefore, the first and third terms cancel. We have only the second term over here left in the final result. It's negative z squared over 2 times the original wave function of the 1s orbital in the hydrogen-like atom or ion. The eigenvalue is this negative z squared over 2, and therefore the total energy of this 1s electron, or you can say the atomic orbital energy, is negative z squared over 2 atomic unit. So that's from postulate 3. How about postulate 4? Postulate 4 takes this form. The weighted average of the value of a physical observable A is equal to this fraction, and on top you have the integral of psi star times this A operator being applied to psi. On the bottom, it's simpler. It's just psi star times psi, and then you integrate the product. Psi star is the complex conjugate of psi. Again, to get the complex conjugate of a wave function, you just need to replace every I with negative I. For a real function, its complex conjugate is itself. So let's look at the average value of the potential energy. First, we need its operator. It's negative z over r over here. Again, this tells you the attraction is negative because we have two different charges. The electron has a negative 1 charge. The nucleus has a positive z charge. The distance is r. Alright, so we need to apply this potential energy operator to the wave function right here. And fortunately, this operation is a simple multiplication. It's negative z over r times psi. D tau, again, is complicated. It's r squared times sine theta times dr, d theta, d phi in the polar spherical coordinates. So we just need to evaluate these two integrals right here. I plug in the wave function. The wave function is e to the power of negative zr here, 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 and here. Again, supposedly this should be the complex conjugate of the wave function. Same here, but again, we're talking about a real function. This part is the volume element d tau. Over here, the volume element d tau. Okay? And this is a triple integral. Fortunately, this triple integral can be decomposed into the product of three single integrals. The first one is the integral of r, and then integral of theta, and then integral of phi. So the integral of theta is actually the integral of sine theta d theta from 0 to pi. The integral of phi is simply just the integral of d phi from 0 to 2 pi. Fortunately, the integrals of theta and phi appear on top and also on the bottom, and they cancel. Therefore, we have just two simple integrals of a function of r. One on top, one on bottom. What's the difference? The difference is very simple. Over here, you have negative z over r. And then we just need to integrate this too. I would recommend you to use Wolfram Alpha. Before we do that, we can use some simple variable substitution to simplify these two integrals. First, e to the power of negative zr times e to the power of negative zr is e to the power of negative 2zr. And then we have this r on the bottom, r squared on top, so it's going to be just negative r here. I put the negative here, negative sign here, and I put this r here. Also, we have a constant z, so I put this z in front of this fraction. Again, the top and bottom look similar, but on the bottom you have r squared here. Now let's use variable substitution. I'm going to replace this z times r, the product of this z and r, with zeta. So zeta equals zr. This is going to be e to the power of negative 2 zeta. This is going to be e to the power of negative 2 zeta. But when we do that, we need to replace this r with zr. We replace this r with zr, this r squared with zr squared, this r with zr squared. So I inserted 2 z's on top, 3 z's on the bottom. It's not balanced. Therefore, I need to introduce another z here. So this z becomes z squared. Now I replace every zr with zeta, and we got this two integrals. Then you can use Wolfram Alpha to evaluate these two integrals. The top, I think, is 1/4, 0.25. The bottom is also 0.25. And then the result is simply negative z squared. It tells you the energy of the 1s electron in the H-like atom or ion is negative z squared atomic unit. So if you have helium plus, the energy of the 1s electron in helium plus is, well, the potential energy of that 1s electron is negative 4. How about lithium 2 plus? Lithium 2 plus has 3 protons. So the potential energy of that 1s electron in lithium 2 plus is negative 9 atomic unit. Beryllium 3 plus, the potential energy is negative 16 atomic units. What about the kinetic energy of the 1s electron? Very simple. The total energy minus the potential energy equals kinetic energy. The total energy is negative z squared over 2, potential energy negative z squared. Therefore, the weighted average of the kinetic energy of the 1s electron in the hydrogen-like atom or ion is z squared over 2. What about other principal quantum numbers? N can be 2, 3, or 4. We can have 2s, 2p, 3s, 3p, 3d orbitals in the hydrogen-like atoms. Well, in that case, its wave function is going to be e to the power of negative z times r over n. N is the principal quantum number. What about the total energy? It's negative z squared over 2n squared. What you can do is you can apply the Hamiltonian to this wave function. The result is going to be this wave function multiplied by a constant. What constant? This constant. This constant, negative z squared over 2n squared, is the total energy of that electron. What about the potential energy of that electron? It happens to be twice its total energy. Negative z squared over n squared. There's no 2 here. What about kinetic energy? It's the total energy minus the potential energy. The result is positive z squared over 2n squared. So you probably can tell this kinetic energy and the total energy happen to have the same magnitude, but opposite signs.